Hey everyone, welcome to a new video, and this is really a follow-on to a video I did a few weeks ago all about Azure Kubernetes Service, AKS. And the biggest feedback I got back was, hey, what about a video going into detail about the networking for Azure Kubernetes Service? How can I offer services out of the cluster? So my goal for this video is to kind of do a deep dive on the networking of AKS, which is really the networking of Kubernetes. So let's kind of just get going. I'm not going to cover AKS, sort of the basics. Go and watch the overview video that I did a few weeks ago. So think about the fundamentals. When I think about an AKS cluster, we start off with the network itself. So we have a virtual network. So we have a VNet, and then within there, we have a certain subnet. So when I deploy my cluster, I deploy it into a subnet. Now later on I'll talk about bringing your own subnet, your own IP or managed, doesn't matter for now. So we have the subnet, and what we're going to do is we have these worker nodes. These are the things that are actually going to host the containers. So I can think about, well, I have kind of node 1, and I might have a second node. We'll kind of do that in a second. Now, on the node, we run pods. So Kubernetes adds the concept of a pod. Normally we just have containers, and then the container, to offer services out, it has to map ports to the NIC of the container host. Then we have to worry about, well, which ports are available. It's hard to do container to container communications. So what we have is we can kind of simplify that. We have the idea of a pod. So we have the pod. Now inside the pod we have containers. So I'm going to think about just like before. Hey, then we have kind of the main container. I can have multiple containers in a pod. In fact, we always do. There's actually another kind of hidden container called the pause container that's in the pod. And it's actually the pause container that owns the namespace. So every pod has its own namespace, a copy of the network stack, its own IP and routing and firewall rules. So this actually has that namespace. Then the other containers kind of use its namespace. The benefit of this is, if something happens to the container, well, the network stack is still safe in that pause container, which is really just pausing for infinity. A new container can spring into life and carry on using the network stack. But I could have additional containers, they're called sidecars, maybe helping that container do its job. But the point is, this pod has a certain IP address. Then I can have another pod, pod 2. Once again, it has kind of a container. Once again, it would have kind of that pause container. That would have kind of IP2. So we have the idea that we have the pods. Pods have an IP address. And what's special about Kubernetes is the rule is that any pod has a unique IP within the cluster, and any pod can talk to any other pod in that cluster using the pod IP address without having to do any kind of network address translation. So if I had another node here, so we say this is node 2, and once again I had some pods running here, and once again inside that there's kind of the container doing the job. This has got IP3, this has got IP4. They can communicate directly with those IP addresses. The rule is they are unique within the cluster, and they can communicate directly using those IP addresses. They don't have to do any kind of NAT, network address translation. So that's kind of the rule. Now these worker nodes, they are running things for Kubernetes, AKS. So you can think about, we have AKS over here. We have kind of, when you think about it, well, we have the Kube API scheduler, we have various controllers, we have the server, we have the etcd database. That's all managed for us with AKS. But what I do have is there's kind of the kubelet, and there's something called kind of kube proxy. And I have those components on all of my worker nodes, and they kind of communicate. If both directions to AKS. So that's what does the management. It helps all these things actually function. These nodes, well, they have IP addresses as well that are on that subnet. Now, this can actually vary, and we're going to get into the detail of that a little bit later on. But the point for right now is I can think about pods have a unique IP within the cluster. So these nodes are part of a certain AKS cluster. That's the rule. The IPs don't have to be unique between clusters. They can't directly talk to pods in other clusters, but within the AKS cluster, any pod has a unique IP address, and it can talk to any other pod without any kind of natting. That's kind of that key rule. So, okay, I said something about, well, I'm drawing these IP addresses are from the subnet, and then I kind of drew these different IP addresses for the pods. And that's kind of one of these fundamental things about AKS clustering, is there's actually different networking plugins that changes actually how this IPing really works. Key thing here, pods always have a unique IP. Pods can always use that IP to talk to other pods in the cluster, even if they're on different nodes. So network plugins, there were two. The one we often think about is KubeNet. So it's kind of very much a standard plugin. And I can think about, once again, we have those same nodes. So I'll just draw two. Obviously, I can have way more than two. And what we're going to have is, once again, we have those pods. Just say they're running 2 pods each. And it gets deployed into a subnet. Now, normally when we deploy from the portal, the network is set up automatically. The IP address range is set up automatically. We don't really do much around it. But fundamentally, there is a subnet here that this is deployed into. Now the nodes themselves, they're going to get an IP address from the subnet. So it's blue, the same color as the subnet. That's where the IP addresses are coming from. Then we have the pods. With KubeNet, the pods do not get their IP addresses from the subnet. In KubeNet, the pods actually have a separate pod CIDR range. This pod CIDR range, I want to pick something that definitely does not overlap. I don't want to overlap with any IP scheme of the virtual network, any network I want to connect to on premises, that's going to mess up that communication. But this pod CIDR only has to be unique within the cluster. So if I had 20 different AKS clusters, I can use exactly the same pod CIDR range on all of my AKS clusters. So the benefit here is, if we think about it, hey, the only real IP addresses I'm using are the worker nodes. And there's also, if I had like a load balancer that was internal, it would take an IP address as well. But I don't need many IP addresses from the real IP space. The pods themselves, they're going to take IP addresses from this pod CIDR range. And again, I'm going to pick an IP range that I'm not using somewhere else. I might pick, let's just say, for example, I should change my color again, 10.244.0.0/16. So I'm picking a great big address space because I'm not using that anywhere else. And I could use that same 10.244 on every AKS cluster I have. It's never going to be seen outside of the cluster. So now the pods, and actually what's going to happen is, each node is going to take a /24 from that pod CIDR range. So this first node will probably take, hey, you're going to take 10.244.0/24. This node would take 10.244.1.0/24. So it's just grabbing that range. So then the pods get IP addresses from this IP range. Does that make sense? So separate range, These IP addresses are not really understood or seen on the real virtual network, but they're just for use inside the cluster. So KubeNet, the key point is the workers get real IP addresses. They're taking up those IPs from the network space, but the pods use an entirely kind of isolated address space. It can't overlap, but I can reuse this same IP space, and it's huge. So I can be fairly wasteful with my IP addresses, which is why I'll just give a /24 to every node. But okay, so how does this pod talk to that pod over there? That IP address doesn't really exist as such. So what we have to do is there's going to be a route table. So we have a route table here. Kind of talk about this as UDR, user-defined routing. And what it's going to have is it's defined at the subnet level. So it will say, hey, look, if I want to get to 10.244.0/24, I have to go to IP1 because it has 10.244.0/24. If I want to get to 10.244.1.0/24, that's that IP space over here, well then you have to go to IP2. So when IP1 of the pod wants to talk to IP3, the traffic kind of goes here. There's actually a bridge, CBR, on each of these nodes. And it says, oh, I don't know what to do with this. This does a kind of lookup. And it says, oh, you're trying to get to 10.244.1.5. Well, it knows 10.244.1.24 is on IP2. So it will hop, send it to IP2, who will then know via the bridge to give it to this particular pod. So I'm going to have this route table, and we can actually kind of see this. So here I'm in the Azure portal, and I actually have two Kubernetes deployments. One is using KubeNet, one is actually using the Azure CNI, which is the other one I'm going to talk about. So if we quickly look at the KubeNet one, there's really one thing I want to draw attention to here. If I look at networking, one of the things we see is a pool cider range. They also have a service cider range. We'll talk about that later on. You can see here my pod cider range is 10.244.0.0. If I look at my Azure CNI deployment, I do not have a pod cider range. I don't have a separate range for the pods, and that will make sense later on. But for my KubeNet, I have this separate range. Now what's happening is, as I described before, that 10.244.0.0 is actually going to get split up between the various nodes. And I have two work nodes. If I look at my node pools, I can actually see, hey, I've got two nodes in my pool. Now if we jump over and actually go ahead and look at the resource group, it created its own virtual network, but it created a route table. If we look at the route table, you can see we have two entries. 10.244.0.0 goes to the first node. 10.244.1.0 goes to the second node. So we can actually see, hey, that's that thing I kind of just drew on the board. When I use KubeNet, it uses a different IP space for the actual pods. Then it uses a route table to enable that space to actually work. So this is also sometimes called actually an overlay network. So that's how that can work. So there's some kind of pros and cons with this thing. Now, I can have up to 110 pods per node with KubeNet. Now you might wonder, well, if I can have 110, why do I give it a /24? That's 251 usable, I lose 5. It's double. The reason for that is if you think about, hey, I need to deploy an update to my pods, if I only had, let's say, a /25, so I had, I don't know, 122, 123, whatever usable IP addresses, I'd have to update a few pods and then delete some, because I've only got a few spare IP addresses. If I give it double the number of IP addresses, then I can essentially redeploy all the pods again, And then once they're deployed, switch over to using the new ones, and then delete all the old ones. Because this IP space is basically free. This is not real IP space on my actual virtual network, it's an overlay. Yes, I can't use it anywhere else, but I can use this same overlay on every single AKS cluster. So I give this a great big IP space, and I'm fairly generous with it. So the benefit of this, if we think about it, is, well, it's very few real IP addresses. So it doesn't take from VNet. If you look at this, if I only had like a /24 of real IP addresses, I could have a couple of hundred nodes and some load balancers. With a very small amount of IP space, I could have a huge number of nodes and then thousands of pods, because the pods want a completely different IP space. Now the downside is there's some extra hops, because obviously now I am kind of doing this lookup, it's bouncing via this. There's a few extra steps involved for that. I have to kind of think about, well, there's a route table there, but Kubernetes takes care of this. It manages that thing for me. So that's KubeNet. Key point. If you remember nothing else, this is the key point. There is a separate CIDR range for the pods. They do not get their IP addresses from the real network. They get their IP addresses from that pod CIDR range. Now our other option is Azure CNI. And it's going to look very similar. Once again, I have kind of my worker nodes. And once again, I have my kind of pods. And once again, I have kind of my subnet. Once again, the worker nodes get their IP addresses from that subnet, just as we would kind of expect. And the pods, well, they get their IP addresses from the subnet as well. So that's the huge difference. There is no CIDR network range. There is no network overlay. The pods, they're getting their IP addresses from the subnet. They could be directly accessed from anything on the network or connected to the network. With this, those pods can't be directly communicated to. They can reach outbound to things on the network, to even connected networks, but things can't get to them directly. That IP address is not usable. Here with Azure CNI, these are real IP addresses. So there's a few changes. So by default, we get 30 pods per node. So that's the default. Now I can increase that. So I think I can configure to actually 250 maximum. Now this is really about the fact that these IP addresses have to actually exist on an object. So these IP addresses actually get placed on the NIC of the virtual machine that is the container host. And I'll show you this in a second. So there's 30 by default. You can increase that up to 250. So the pro of this is the pods are directly contactable. I can from anywhere just go and talk to the pod. The negative uses the real IP space. If I have lots and lots of pods, I need to have a really big network range I can use for my cluster. This cannot overlap with other AKS clusters. These are now real IP addresses. So if I have a finite amount of IP space I can use, and I wanted to have hundreds and hundreds of pods, well, I have to do the math. If I had, let's say each node, let's say I increase that to 100 pods per node. So for every node, I'd need 100 IPs for pods, and then one for the nodes, so 101. You need some spare room there, times the number of nodes. I might need 5, 6, depends on how many nodes I have, hundreds and hundreds of real IP addresses. Whereas remember with KubeNet, I just need really a real IP address per node, and then load balancers, same as over here. So that's really the key difference about this. KubeNet. Pods take their IP addressing from a different space. That's the key point. But there's a slight perp hit because there are these hops that have to happen. I have this route table to make that work. And we kind of saw that. We saw the route table. We saw how I divided it up into /24s. With Azure CNI, I don't have that. For Azure CNI, they're real IP addresses. So if we jump over again to the portal, so if I go and look at my other cluster, so if we look at the non-KubeNet one, once again, remember, we look at the networking. What do we see? There is no pod side range. It does not have it. If we then go and actually look at the actual configuration, what that is, and let's say we go and actually look at the virtual machine scale set. It's using a virtual machine scale set to create the nodes. It makes it easy to scale them. And if we look at the instances, remember I said there's 30 by default. So if I select one of them, then look in the networking of it, if I look at the IP configuration, wow, it has 31 IP configurations. 31. Because one, for the worker node, then it's basically reserving 30 for the 30 pods it can support. As I create pods on it, that kind of bridge inside would then map these to various pods, so it can actually, the traffic can flow through the network and it can then pass it onto the pod. So that's kind of the key difference. I actually have all those IPs on the NIC of the container host. So they're real IPs. It's pre-allocating them in advance. It doesn't have to mess around as I create and delete pods. That's why we have to tell it the max number of pods we're going to support on the node. It's going to pre-allocate all of those onto the NIC of the container host, that Kubernetes worker. So that's kind of that key difference right there. Separate pod, side range, pods get their IP address directly from the network. So if I think about what I just said, you fundamentally have the network plugin. Let's actually zoom in a little bit. There we go. We have the network plugin. And then after network plugin, we kind of have the subnet configuration, the IP. And I can think about, well, there's KubeNet, and there's Azure CNI, Container Networking Interface. And then there's managed, i.e. it's going to create the virtual network, it's going to pick the IP space, it's going to do everything for you, or kind of bring your own IP. I've created the VNet, I tell it what to deploy to. In the portal, if I go to Kubernetes and I say add a Kubernetes cluster, and I have to kind of quickly fill out all of these details. So I'll just super quick, just so we can go through this. Resource group doesn't matter, I'm not going to create this. Name doesn't matter. Load pools doesn't matter. Authentication doesn't matter. Network configuration. What do we see here? So in the portal, we see basic. It's not really asking us any questions. Or we see advanced, where it can create a new network, or I could actually go and select an existing one because of the region. I don't have an existing one there. It lets us pick the IP address range. Notice there's no pod IP range because advanced is going to use Azure CNI. Basic is going to use KubeNet. So while the portal just has this basic and advanced, what that's really mapping to is basic, it's picking these two options. When I pick advanced, it's picking these two options. So the portal is driving you that way. If you pick basic, it's going to use KubeNet and it's going to pick the IP range. It's going to create a new VNet. If you pick advanced, it's going to use Azure CNI and it's going to either let you configure to select a new virtual network, or you can select one. But I can use any combination I want. Outside of the portal, I could absolutely say, hey, I want to use KubeNet, but I want to bring my own IP space. I want to use KubeNet, but those worker nodes, I want to deploy it into an existing subnet I already have in my existing virtual network. I don't have to have it use a managed IP space that it creates itself. I can select what the pod range is. Likewise, I could say, hey, I want to use Azure CNI, but you go ahead and create a new VNet and you manage those things. So I can absolutely use any combination of KubeNet with managed or bring your own, and Azure CNI with managed or bring your own. In the portal, basic maps to KubeNet and managed, advanced maps to Azure CNI and bring your own. But you're really not limited to that. Okay, so that was all how things can be configured, what the networking looks like inside that AKS cluster. Now I want to actually get things outside the cluster. So if we think about, let's just say we have some pods. So we'll say we have 3 pods, and they're all offering the same service. I could use any of those pods. And we might think, okay, I will just then point to those pods via an Azure load balancer. There's actually something in between. You might remember in the portal, when we looked at the networking of one of these Kubernetes services, we actually saw something called the service side of range. And this was 117.16/16. This is only visible inside the cluster. Again, it shouldn't overlap. So just like the pod side of range, if I had one with KubeNet, it should not overlap with any real IP range you're using because it will cause conflicts. But I can use that same range on every single AKS cluster. And what this server side of range is used is for service IPs. Sorry, service side is used for. You might also hear them called cluster IPs. So we have this, and we have this on both KubeNet and Azure CNI. It's always there. This is a Kubernetes core kind of construct. Because when I do a deployment, what actually happens is as well, is there's kind of a service is put in front of it. So I can think about, hey, I'm doing this deployment. It's going to create service 1 in front of all these pod 1, pod 2, pod 3. This service gets an IP address from that service side of range. So again, this is only accessible from inside that AKS cluster. So any node within that cluster, any pod will be able to talk to that service IP. So that's kind of a reliable IP. It's going to be the same. Pods might float in and out of existence constantly. They might just run a job and then die. Run a job, die. If I'm trying to talk to a service, I don't want to worry about these IP addresses maybe constantly coming in and out of existence. I want some reliable IP address that may also map to a DNS name that I can always talk to, and then it worries about what the pod IP addresses are that again might be constantly changing. So this service effectively points to these kind of endpoints, these pods that are offering, actually enabling that service to function. Now what the service is doing, so again the service is from that kind of, that service side of range. That's where that is coming from. Again, it's only from within the cluster, so big point, only in cluster. So an Azure load balancer, for example, could not point to that IP. It doesn't exist outside the cluster. I can't use that directly. So I have that service IP, and what's going to happen is this does a very simple kind of round robin. So as the request comes in, it's going to go to P1, pod 1, then pod 2, then pod 3, then pod 1, pod 2, pod 3. So you're going to think, hey, it's a round, a very round robin. I can't draw. There we go. It's a round robin. Red chest. There you go. So round robin, it's going to distribute that way. So it's doing a fairly basic distribution, but that's really all. But it knows if they're there or not, because remember, Kubernetes is the one that's checking, hey, are pods there? It has a deployment that says, hey, I need this many pods. It updates the service with the endpoints as these come in and out of existence, as the IP addresses may change, because P1 disappears and P4 pops into existence. It's going to keep that service up to date. So this IP address here is essentially static. It's not going to change. I can always talk to that service via that IP. So why this is super useful, imagine I have a multi-tiered service. So I have some other pods, same cluster. Maybe this is pod 4, pod 5, pod 6. They might also have their own service. So they've got a kind of service as well. They have kind of an IP2 from that same service range. This distributes between those. So if pod 4 wants to talk to that service, well, pod 4 says, hey, I need to use your service, and it says, okay, go to that one. If pod 2 needs to talk to this service, well, it goes here and it says, okay, well, you go to that one. It's handling that distribution and enables these to not worry about those pod IP addresses. So it gives me kind of that great capability. Now, what's actually happening is there's something called the kube proxy. So we have kind of this kube proxy component we drew at the start. So all the way at the start, we kind of drew, there's the kubelet that kind of talks to the AKS server, the API server. There's also this kube proxy that enables a lot of the networking capabilities. Well, this is where it comes into play. When I get this thing coming into a service, the kube proxy goes and looks at the service and says, okay, well, these are endpoints on that service. I need to go and distribute a certain way. So it's going to make that happen. So now within that actual AKS cluster, these can communicate that way. And we can actually quickly see that. So what I have here is that this is actually the Microsoft kind of example file. It's a voting app. So it has a back end and it has kind of a front end configuration to it. So if we quickly kind of look, that back end has a service. And it's just a kind service. We can see it there. It's just operating on a certain port. It also has a front end. Well, that's of kind service, but then we actually see, well, the spec is a load balancer, and we'll talk more about that later on. But if we focus on that back end, well, that is just of kind service. If we actually looked at our cluster and said, hey, show me my service, I can see that back end has a cluster IP. So that cluster IP came from that service side range, that first one right there. There's no external IP, it doesn't map to anything outside the AKS cluster on that port, and it would then distribute to the various endpoints, i.e. that single pod. That's what it would actually go and communicate with. And when we get to the actual front end one, the load balancer, I'll show a bit more detail about actually, hey, how do we map to those endpoints? But that's the point of it. So that service IP, that also known as a cluster IP, I can use that within the cluster to find those services that are hosted by various pods. Okay, well now I want to take that service and make it available outside the cluster. It's a front end configuration. I need to make it available. And remember, that service is only visible if you're inside the cluster. That's a key point. That service side range is not visible. There's no route table using it. It's only internal to the cluster. Only things in the cluster can see that service IP and use it. So if we take this then, so let's take those pods again. So we'll say we got the 3 pods. And we know we have kind of a service fronting it. And we know that service has kind of an IP address. And once again, kind of we have the pod 1, pod 2, pod 3 that have IP addresses, but I'm not going to super worry about that for now. Now the reality, the physical structure, remember, is they're running on nodes. So we have, let's just say 2. Doesn't super matter. But let's say I have 2 worker nodes. Both of these are running kind of that kube proxy. So both have kube proxy. And both of these have an IP address from the actual network. Now the pods may have an actual IP address from the network as well. If it was Azure CNI, if it was KubeNet, they would be internal. Doesn't change anything about what we're going to do here. So we don't care. Because of this service IP, what's happening behind the scenes doesn't change anything. You might think it does. It doesn't. Nothing changes from this point on. KubeNet and Azure CNI is only really about how we worry about the IP allocation of the pods, where they come from. It does not change how load balancers work, how Nginx works, how App Gateway works. They all function the same regardless. So you don't really have to worry about, hey, is this KubeNet or Azure CNI from this point on. So we have the pods, we have a service. Remember, the service can redirect round robin to one of those 3. And now I want to make it available externally, external to the cluster. And the first way we're going to do that is with the Azure Load Balancer. So we have kind of the Azure Load Balancer. Remember, the Azure Load Balancer has a front-end IP configuration. That could be a public IP address, or it could be an internal IP address, i.e. coming from the subnet. Again, it doesn't actually change anything. Then we have to have a back-end pool, remember? So what do we think the back-end pool points to for our Azure Load Balancer? Does it point to the service IP? We can't. Service IP is only visible inside the cluster. Does it point to the pods? Well, then what's the point in having the service? Now I'm back to worrying about if a pod comes in and out of existence. The load balancer would have to get updated every time. So what does the backend pool point to? Backend pool points to the IP addresses of the worker nodes. You might think, oh, wait a minute. Follow what happens. Let's say these are offering a service on port 80. I'm just making it up, but let's say it's port 80 is what we're offering a service on. So the service knows, hey, there's a service on port 80 as well. Traffic comes into the front end IP, port 80. Sends it over to here, port 80. Kube proxy at this point. So it comes into a worker. It doesn't matter if there's a pod for that service on that particular worker. It doesn't change anything. It doesn't matter where the pods are. If I add 10 worker nodes, all 10 will always be in the backend pool. The backend pool is every node in the AKS cluster. Even if I add 1 pod, the backend pool points to all 10. Because the load balancer is doing health checks as a probe, which just uses a different port. The traffic gets sent to it. Kube proxy grabs that. Kube proxy grabs it. It knows what the front end IP is, and it says, hey, front end IP X. Front end IP X maps to service 1. So it will then take that via the bridge, send it to the service 1. Service 1 does the round robin, says it will go to pod 1. So the traffic flows. The kube proxy is kind of that magic that does the service lookup because it knows the front end IPs. Remember, I might have multiple services, multiple front end IPs. But kube proxy and the services know based on which front end IP the traffic is coming in from. Now, this took me a second to get my head around. When we do a deployment, we have a manifest file. So we have this YAML file, which has got the description of all the things we're deploying. Okay. Now, where do we deploy that to? We don't deploy it to Azure. We deploy it to Kubernetes, in this case, AKS. So we have that Kubernetes, we have the API server, Kube API server. AKS then goes and makes it reality, Kubernetes. Now in this case, because as part of my configuration, if we actually go and look, this time, if we go and look at my file, we'll do an example of this, and we're going to follow this kind of through. I had a service, but the type was load balancer. So this was sent to Kubernetes. So Kubernetes gets that config, it goes and creates the pods, it goes and creates the service, does all that other stuff, but then it went and created the load balancer. It knows what front end IP was given for that load balancer. So now when the traffic comes in from this front end IP, kubeproxy can look up and say, hey, front end IP 1, front end IP 1, well, that's service 1, go and redirect it, because now it's inside the cluster, because the worker nodes, they have the bridge, the kubeproxy, it can now get to the service, hey, service 1, go and round robin it between the nodes. That's kind of the magic thing that's happening at this point. So I've actually got that deployment. So remember, I had that load balancer option, and notice it had an external IP, 40.124.88.5. You'll see there's port 80. There's also a second port, and this is actually used for the health probe, because when the load balancer is doing the health probing, it's not coming from a front end IP. So that's kind of called a node port, and that just maps directly through and relates to that service. So when we look at our commands, we say, okay, if we look in detail at that front end configuration, I can see, okay, yeah, the load balancer ingress, so it knows traffic coming from 40.124.88.5, yep, that's for this service. The target port is 80. And then we have that node port, which is only going to use for the health probe from the cluster. I can also look at the endpoints, and notice it points to, the front end pod to port 80. If we jump over to Azure, and we actually go and look at the resource group that it deployed all its stuff to. Now, there's an important point about this. So this is actually running as a service principal. So that service principal has to have rights to go and create those objects. Now, the default it uses and that it creates, it has the rights to do that. If you try to deploy to a different virtual network, you need to make sure you give that service principal the right permissions so it can actually go and create these things. So notice here, I've got a load balancer. And if we look at the front end configuration, I'm actually going to have two. This first one, this is actually used for outbound. So this is there regardless. If I don't have any load balancer, it creates a load balancer and it uses that for outbound kind of natting, so it can go and get to things outside the cluster. So that's always there. But you see this second one, well, there's my 40.124.88.5, 40.124.88.5. So that's the actual front end configuration. Okay, so let's see if I'm a liar. I'm English, I'm normally a villain. What is the back end pool pointing to? Remember, I only have one pod. I have two nodes in this cluster. Kubernetes, two virtual machines. It's pointing to the worker nodes. They are the IP addresses of the workers. It is not pointing to the service IP. It's not pointing to the single pod. It will always point to every single node in the cluster will be part of the backend set. Because it can send the traffic to any of them. It doesn't matter if the pod's there or not. It sends the traffic to any worker node. At that point, hey, kubeproxy will look at it, knows what that front end IP is, can map it through to the service. From the service, find out which pod are you going to round robin to, and then that worker can go and make sure the traffic gets to that particular pod. Now, if we look at the health probe, this is where it's using that node pool. So it's just using it so it doesn't have to do the full service mapping. But the actual load balancing rule is just direct. Hey, my rule is from this front end 80, you can see to the back end 80, and it's using that health probe. So that's kind of that full configuration there. You You can kind of see that all the way through. So that's where that was an external IP. As part of our configuration in the YAML, it was a load balancer. So again, remember when we look at our services, our service is saying, hey, it's an external IP. Now it's just external to the cluster. I could change this to be an internal load balancer. So if I delete that annotation and save it, and then if I apply that again, so I'm just changing it from external to internal. Oh, I'm in the wrong folder. Let's go to AKS quickly. There we go. And now if I run that file again, okay, there we go. I had an extra weird character now. So now it's gone and configured. Notice it's saying, hey, configuring. So it's going to change that load balancer from an external to an internal. Now it's going to be pretty quick. If we look at the service again, still saying external IP. What's actually happening behind the scenes as well is, remember we just had a single load balancer before. If we go and look at our group, we just have this single load balancer. Now what it's actually going to do now is it will create a second one. There we go. So it's created an internal load balancer. So the internal load balancer is just a front-end IP configuration. It's going to be an IP address from the subnet, but it's still going to have both the nodes as the backend set. Notice we still have the external load balancer because remember now it's just doing that outbound natting. So it has that outbound rule to enable us to go and get to things. It's enabling the pods to go and get to things outside of the cluster. So we still have that. But now it just flipped over to an internal. And now if we run this again and look at the service, there we go. So it's still an external IP to the cluster, but now it's 10.0.1, but it still knows. So it doesn't change anything about our traffic flow. The traffic flow is still going to come in to that IP. The service knows what IP, and it will flow through. So that's how we work with the Azure Load Balancer. Yes, we have the service. Yes, we have the pods, but we're actually going to any of the worker nodes, and then via the kubeproxy does the lookup, sends it through. So that's how we're essentially working with the Azure Load Balancer. And that's a very common one. You're going to see that happening most of the time. But what is the Azure Load Balancer? That's kind of a layer 4. So we understand TCP and UDP, but I have zero clue about HTTP. I have zero clue about path-based routing or SSL offloader. I can't do any of that stuff. And we might want that. Especially if this is port 80 or 443, I'm doing web stuff. I probably want a more intelligent type of balancer there. And when we talk about more intelligent balancers, we're probably thinking about Nginx or Azure App Gateway. So what changes when I want to use Nginx or App Gateway? So we're going to have the same stuff again. So we'll start with Nginx. Nginx is probably the most common, kind of like, and these both layer 7. So they understand HTTP, HTTPS, those things. There's Helm charts all over the place for Nginx. It's really kind of the default most people use. So I can think about, okay, I've got exactly the same situation again. I've got my same pods. I'm not going to read all this in any well. I've got my same kind of service with a service IP. And now I want to make it available externally through something else. And remember, I've still got my worker nodes kind of sitting here. So with Nginx, what happens is we're going to do a deployment of Nginx. And Nginx actually deploys into pods. Now, so I've got kind of a deployment, an Nginx deploy. And it's going to create multiple Nginx pods. So these are all running Nginx inside them. I'm going to have obviously multiple ones for scale and resiliency, etc., etc. So I've got that deployment. And guess what it's going to do? It's going to stick a service in front of it. So it's going to have a service, and that service is going to have a service IP. Now you're going to say, wait a minute, okay, service IP is only available inside the AKS cluster, so that's useless. It's not going to let me get anything in. So remember that redirects to one of these, and then the Nginx's can actually go and then talk to the service. But they're doing that intelligent. They understand layer 7, so they can do things like that path-based routing. They can do SSL offload. They can do all the great things I can do at layer 7. But what we actually have to do is in front of that, I have Azure Load Balancer. Again, I have the front end IP. The back end is what? Is the nodes. Same as before. It's this. It's this exact same picture, except there's another service now in front. That service is running Nginx. Because Nginx is now, this is just doing very basic layer 4. Nginx can now do the good stuff at layer 7. So it's getting the traffic. This is going to kind of do that round robin to the different Nginx instances I have in that deployment. It can now understand, oh, path-based routing. Okay, so this one should go to this service over here. This path should go to a different service. So I've got all these different kind of services. I can kind of delete this one service idea. I might have, and that's when you'd want to use Nginx. I've got tons of different services going to tons of different pods on the back end. So now it can do that great kind of path-based routing to work out, well, based on this path and this information, go to this service or that service or anything else. The traffic comes in, load balancer, basic layer 4, just sends it to the worker node. Kubeproxy does its job, say, okay, this is destined for the Nginx service, which sends it to one of the Nginx pods. Then it does all that intelligent stuff inside, can send it to all of the various services. Because these are in, remember, the cluster. These Nginx pods are inside the cluster, and that's kind of the key point here. So these Nginx things here are what we call ingress controllers. Because they are inside the cluster, they can talk directly to those service IP addresses. Whereas if Nginx was out here, it couldn't. It wouldn't be able to talk to them. But now it can. So it can actually go and have all of those different communications with all of the different service IPs and do that kind of configuration and do that routing. So that's why we have them. That's why we have these pods inside the cluster. So the traffic can come in, it can do the intelligent lookup, and then it can communicate with those service IPs that are normally only available. So we have multiple pods for HA for scale. Now the great thing is we then get all of that functionality. So we can do things like path-based routing. I can do things around SSL. I can do all those great layer 7 things. I do have to, maybe a negative thing, I am having to kind of maintain and scale Nginx. If I increase the number of apps, I'm doing more stuff. I need to make sure I have. Now it's easy to scale in my deployment file. I can scale those things up, but I am thinking about that. It's saying I'm managing. So it's great functionality. I'm maintaining it, and obviously it's using up resource within my worker nodes, but it's resource I'm already paying for. I'm paying for these worker nodes. So that's Nginx. Key point, it's got things inside the cluster so they can talk directly to the services. Okay, so what about App Gateway? And I'm always scared to talk about App Gateway because it kind of takes everything we've learned and turns it on its head a little bit. We have the same config. We have kind of our pods. And we do have there's still the service there. We still have our kind of worker nodes kind of spanning the service, sort of goes across the different worker nodes. So we still all have that great stuff. Now remember, I have that YAML kind of configuration. And in that YAML configuration, now, in the other one, I had an engine of Nginx. Now I'm saying, hey, I want to use app gateway. And I'm saying, hey, for this path, I'm doing path-based kind of routing here. This path goes to this application. So I've got a YAML file that's doing configuration. And remember, where do I apply this to? I apply this to AKS. So Azure, remember our Azure Resource Manager lives over here. It's how we configure everything. Has zero clue about any of this stuff. But now I want to use App Gateway. And remember, App Gateway, let's say it's sitting out here. Actually, we draw it blue. Too many colors. There we go. We'll do this in blue. So we've got App Gateway over here. So we can think of the icon. It's kind of going that way. So we've got App Gateway. That's configured via Azure Resource Manager. I have this YAML file that I'm saying, hey, I want this particular path to go to this particular app, i.e. this particular service. And that configuration gets pushed through to the nodes via the kubelet, kube proxy, all that's happening. Fantastic. How does App Gateway find out about any of that? Now I could use App Gateway and just make it point to, in an infrastructure mode, and make it point to a load balancer. So App Gateway is just fronting and then it sends it to a load balancer, and the load balancer is making things available. So I can have App Gateway out here pointing to a load balancer. If I actually want to do an App Gateway integrated, well, there's a problem. How does this find out about these rules that happen? So when I deploy App Gateway to an AKS cluster, it creates a pod, just one single lonely pod that is kind of this App Gateway config. Now I'm writing config because it is not an ingress controller. Traffic is not going to come in and then go to the service IP. I need a lot more than it doesn't scale. This job, its only job, is as these configurations are applied, its job is to kind of read that configuration as it comes in. So hey, this new path to this app, its job is to look at that and find that out and translate that into ARM commands so the gateway can get configured to know that, oh, well, kind of this path should go to that app. So that's why there's a pod. So when I deploy App Gateway, it does create a pod in the cluster, just one. Doesn't matter how many worker nodes, it's only one. Because all its job is to sit there and wait for config to come in, read the config, translate it into ARM commands so we can update App Gateway. If it died, big deal. AKS will deploy a new one in its place. So how does the traffic get there then? Because App Gateway can't send to the service, because remember the service IP is internal to the cluster. Normally I would kind of expose something maybe via the pod, the worker node. I'd use kube proxy. Doesn't do that. What does App Gateway point to? And this is kind of the scary part. App Gateway points to the pods directly. So completely different than anything else. It does not use the service IP. It uses it in a very basic way because this App Gateway config checks to say, oh, what pods are behind the service, so it can configure this with the right pod IP addresses. But it is not sending it via kube proxy or anything else. It's sending it directly to the pods. It's because of that it did not support KubeNet for the longest time. Because remember, with Azure CNI, these pods have real IP addresses on the subnet. It would be easy for App Gateway to send it directly to the pods because they have real IPs. So it didn't support KubeNet. Now it does support KubeNet now. And the way it supports KubeNet now, which seems kind of surprising, is if you think about it, when you deploy App Gateway, you actually deploy App Gateway to a subnet. Now remember, these workers are also sitting on a subnet. And remember what we did is to make KubeNet work, we had a route table. And the route table said, hey, for these IPs, you have to go to this IP address. So the way you make App Gateway work with KubeNet, that route table, you give to it subnet as well. So now App Gateway knows, hey, to get to this internal pod cider IP address, oh, I've got a copy of your route table. Oh, I know to get to pod 3's KubeNet cider IP, I have to send it to IP2 of the worker, and then it will go and send it through. So that's App Gateway. So in review, we have multiple pods behind a service that's only available inside the cluster. Azure Load Balancer points to the worker node's IP, which then kubeproxy grabs the traffic, does a service lookup, does a round robin to the services. It's layer 4. Nginx, and there are many others. Nginx is just one, but it's a very common one. They're all going to work in a very similar way. They have ingress controllers. So they deploy pods into the cluster so it can then talk to all the different service IPs. That is fronted by its own service. The Azure Load Balancer points to the worker node IPs. Again, kubeproxy grabs the traffic, looks at the service, round robins it to one of the Nginx ingress controllers, so the traffic actually get the traffic, so it has to scale. It then does its layer 7, whatever goodness, sends it onto the service, which round robins to one of the pods behind that service. App Gateway, different than all the others. Yes, it has a pod. That pod is only there to check the config. Get the config, configure the App Gateway, and then the App Gateway points to the pods directly. If it's Azure CNI, that's easy. These have real IP addresses. If it's KubeNet, it takes a copy of the route table on that subnet, which enables it to work, remember? It has those lookup rules, and applies it to the subnet of the App Gateway. And if we review all the way back, the fundamental difference, remember, between KubeNet and Azure CNI was simply in KubeNet, the pods use an overlay network. So I don't have to worry about my real IP address range on my network. I can have tons of pods. I don't need many IPs on my real network. There's a little perf impact. They're not directly accessible. But I can use that pod cider range over and over again on my different clusters. That service cider range I can use over and over again. It just has to not overlap with real IPs. But both the pod cider and the service cider can overlap with other AKS clusters. Azure CNI, the pods get their IP addresses from the actual subnet. So there's an IP address challenge there potentially. If I have lots of pods, I'd need a big chunk of IP space to handle it. So that was a big video. I hope this was useful. I hope it cleared things up. Again, I try to kind of show the demos and show these actual constructs to kind of drive home. These samples are available on the Microsoft Docs, so deploy it yourself, test it out. And if this was useful, please like, please comment, please subscribe. And until next time, take care of yourselves.